All right, section 4.3 is called area, and in terms of a picture, what we're going to be doing in this section is we're going to be taking a curve, and it could look like a line even. It doesn't have to look actually curved, but we're going to take in general a curve, and what we're going to be trying to do is trying to take this location, wherever it starts and wherever we're ending, and those points are given to us if they're asked to be used, and we're going to try and find sort of the image you have is the area under this curve between A and B. So if we were to shade this in, obviously it's an unusual shape. It's not just something we can calculate by doing length times width or something like that. It's got this curved feature on the top of it. But even though we can't calculate it exactly by doing length times width, like for an area of a rectangle, what we can do is we can approximate this area using rectangles. So in the idea, or the idea would be that we're going to call this one x0, and I'm going to draw the picture as though there's 4 rectangles. There's nothing special about 4. It's just going to draw my picture really quickly so that we can move on. But if we were to sort of subdivide this into 4 rectangles, so the first location I called x0, this one would be x1, x2, x3, and then we call the last one where the b value was x4. We can imagine taking those intervals that I've sort of created and creating a rectangle. But there are 3 ways to create that rectangle. We could either use the left end point as the height of the rectangle, so right here, and then draw that height across and then down. Or we could use the right end point and draw the height across like this and then shade the rectangle down. Or we can use the midpoint and draw the rectangle and shade it all the way down. Those are the 3 different approaches. Okay. One thing to be aware of is that these rectangles are all the same width. Okay. There's nothing special about doing it except that it's easy to work with. I mean, we'd like for it to be easier to work with, so we are going to make them the same width. The width, we're going to call that is delta x, just a change in x. And in general, what this is it takes the end point interval, so in this case B and A, or you could call it x4 and x1 or x0, and you divide by however many rectangles you're working with. So in my picture here, I made 4 rectangles, so the width of these would be B minus A, the width of the interval, divided by 4. Now, we're actually going to draw this same image, but more specifically using the 3 different types of rectangles. So here's the first one we're going to do. We're going to draw this image using left rectangles and talk about how we go about calculating the particular area that we're looking for. So here's my actual region from the first point to the last one, and I'm going to call them x0 to x4 because it'll be easier to write the notation in a moment. It'll be clearer. And we're going to make 4 rectangles. Again, there's nothing special about the number 4. It's just going to lead us to the same image on all 4 of them. So these would be x1 and x2 and x3 in the middle. And the first thing we're going to do is we're going to use the left end points. So my left end point for my interval between x0 and x1 is actually at x0. And if we draw this across and down, we get this image for my first rectangle. If we use the interval between x1 and x2, then the left end point is the value at x1, and so we're going to draw it over and down. Now, obviously, you can tell that this is not a perfect image. Both of those two, anyway, are overestimates of the area, right? I've got too much that I've shaded in. I've shaded in extra that's not really under the curve. But by the same token, if we have the curve going upward over here between x2 and x3, you can see that sometimes it actually underestimates the area. And we didn't get quite all of the area under the curve by using this rectangle. And then if we go from x3 to x4, using the x3 endpoint, the same thing sort of happens again. We have this underestimate of area. Now, this is an approximation. Now, think about with me, is there something with this particular picture, using the left end points, that we could do to make this a better estimate? Can you imagine? what could we do to sort of limit the amount of error that we're getting?
Use the left endpoints for the first two and use the right endpoints for the second two?
Sometimes in a shape that might actually be helpful to switch the endpoints. It's very complicated to do that in terms of the notation, though.
Have more rectangles.
If you had more rectangles, this would actually solve the problem. Again, it becomes more complicated with more rectangles, but if we had more rectangles, it would also be another way that we could get a better estimate. We'd have less overage and less underage, if you will, or being under the curve on the shape that we have. So yes, more rectangles is kind of going to be where we're going to head in this approach because it keeps things consistent throughout the intervals. Now actually calculating this area, your book is going to use the letter L. So this function L of x to calculate the area of these four rectangles. Now imagine if you were to do this, how do you calculate the area of a rectangle? Length times width. And what is the width of every one of these rectangles? They're the same. It's the b minus a over 4. So we called it delta x a moment ago, and I used b minus a. Since I've got x4 and x0 here, I'll use those here. But it's called delta x. It's the width of the rectangle. And so delta x on the first rectangle, I'm using this one first, is going to be the width. How do I get the length or the height of that rectangle? Visually, what's the height?
F of x.
Yeah, it's the curve that I'm on at a particular point, in this case the left end point. So the height of this rectangle is determined right here by this coordinate pair. That ordered pair is the height. In particular, the y value. So this would be f of x0. So this is the width, delta x, times the height, f of x0. And that's the first rectangle. How about the second rectangle? What's its width?
What is L of x?
This is what your book's notation is going to be for the area using the left endpoints. L for left. That's what they're doing. Yeah. I wouldn't say that that's like highly consistent among all textbooks or anything like that. I'm not sure that I've seen that notation used before, but it's fine. What's the width of the second one? Delta x. What's the height? Yeah, it's f of x1. What's the width of the third rectangle? Delta x. What's the height? F of x2. What's the width of the fourth rectangle? Delta x, right? Yeah. Delta x. And then the height? F of x3. So you notice that we don't have an f of x4 because we didn't actually use that particular coordinate pair as a height of any rectangle. There's nothing wrong with this expression, how it's written out, but there is a simplified way we could write it. You notice there's something in common in every single one of those terms, right? Yeah, it's that delta x. So I'm going to factor that delta x out. And if I do that, I'm just adding the four heights together. Now, in terms of actual computation, this is very handy. In terms of writing out the expression, if I had, say, 16 rectangles or whatever, I don't really want to do that. There is a condensed way to write this that you're going to see as being somewhat familiar. So this is delta x times the summation from I equals 0 to 3 of f of x sub I. That's the condensed notation for what we're doing. And starts to look a little bit like what we did in section 4.2, right? All right, so this is left endpoints. And if we can do it for left endpoints, we could certainly do the same argument for right endpoints. Agreed? So let's take a look at what that would look like, or what the difference would be between the right endpoints versus the left endpoints we just did. Still starting at x0, still ending at x4. And we're going to still draw in four rectangles for our argument. Except that on the first rectangle, instead of using x0, or the function at x0 as my height, I'm going to use the function value at x1, because I'm supposed to be using the right endpoints. So this would be the interval between x0 and x1, the value x1 is on the right-hand corner. So this would be the rectangle that I would get. And then between x1 and x2, I'd use the height at x2. Between x2 and x3, I'd use the height at x3. And between x3 and x4, I'd use the height at x4. So I get this image. Now, this is a kind of symmetric kind of a curve that I've used, so it sort of looks like I'm going to get the same value. I've got about the same amount of overage as I have underage from the last example and so forth. I'm not too concerned about that. Any idea what your book might be calling this area? They do. They call it R of x. And we can write out, just like we did last time, all of the widths times the heights. But can we cut to the chase and recognize I can factor the widths out just like last time? So I've got this delta x, and I've got these heights, but what is the first height that I have? F of x1 this time. And what's the last height that I have? Yeah, we actually get f of x4 on this particular height. And notationally, in terms of the summation notation, this would be going from I equal 1 to 4 of f of x sub I. Now, in practice, if you've already found the left endpoint approximation, it's really easy to find the right endpoint approximation. You just leave off the f of x0, and you add in the f of x4. Right? I mean, that's the only difference in these formulas is whether we use x0 or x4 in the calculation. So calculating one to the other is a pretty quick change in the calculation. Okay, the third one is a little more complicated to write down, but in general, it gives us also a better approximation than the other two. Okay? Depending on your curve, that might not always be the case, but in general, it will give you a better approximation. So this one is going to go from x0 to x4 like the others. And we're going to draw in 4 rectangles just like on the others. Now, instead of actually using a left endpoint or the right endpoint, we're going to use the points in between, the midpoint. So halfway between x0 and x1 is what we'll use to determine our height. And most books don't give it a name, like another subscript name. There we go.
Is this going to be M of X?
Yes, that is what they usually do. Your book is not actually right. Yeah, your book actually doesn't write it out, or at least I don't have it written in my notes, which means it probably didn't write it out when I created the notes for it. But you can imagine each of these intervals in between, we're going to actually calculate them one at a time, and we're going to use their heights instead. So if I gave them other names, we could do this. I'm hesitant to do that because your book doesn't actually give them other names, but this location, this location, this location, and this location would be my function values that I would be finding the heights for, that I would add together. But then notice the width of the rectangles is still delta x, which is x4 minus x1 plus x1 over 4. I said it wrong. Minus, there we go, over 4. So, oh, it's x0. My bad. All right, so it's still the same width of the rectangles. I don't have 8 rectangles here. I still have 4 rectangles. They're just being determined by the point in the middle instead of the point on either end. All right, so I want to do an actual example so you can see how this works. It's not a terribly complicated process, but it's a little bit tedious if you have a lot of rectangles. The one that we're going to do this for is only going to have 4 rectangles, so it's not going to be too bad. So we're going to approximate the area under the curve of the given interval using n rectangles. In this case, our n is 4. And the evaluation rules using left endpoints, midpoints, and right endpoints. So we're going to calculate 3 quantities. And they're all going to be close. I mean, they should all be approximations for the same quantity. That is the area under this curve. So there's nothing special about, or nothing specifically different that should, like if you get answers that are vastly different, there's a problem. That's what I'm trying to say. Your answers should look similar, okay? So let's take a look at this. As you're doing this, it might be helpful to take a look at the graph of this between 0 and 2. So just for the sake of having a picture to draw upon, what does the graph of this look like?
Parabola.
It's a parabola, opening
Upward.
upward. What does the plus 5 do?
Moves it up 5.
It moves it up 5. So we're actually going to be graphing this starting sort of like at 5 on the y-axis and going up from there. I'm supposed to be graphing this or evaluating this from 0 out to 2. And I'm supposed to be drawing 4 rectangles. So at the very least, it would be helpful to draw in this kind of an image when you're working on these. Okay? If you don't want to draw the image, you at least should probably draw the x-axis where you subdivide the intervals to make sure you're getting the right coordinate, endpoints for everything. So for my intervals right here, I've got 0, 1/2, 1, 3/2, and 2. Or you can use decimal approximations if you prefer. Everybody good so far? I'm going to show you how to use your calculator to help you with this too, but let's take a look at writing out what the interval looks like. Left endpoints is what they asked me to calculate first. So this is L of x. What is the width of each of these rectangles? 1/2. Can you see it okay? Width of 1/2. All right. And then I need to add up the 4 heights using left endpoints. What is the first left endpoint? F of 0. And then the second one, f of 1/2. The third one, f of 1. And the last one, f of 3/2. All right, so grab your calculator and let's actually look at how we can calculate this without too much strain or error because we approximate something too soon. We don't want that either. Oops. All right, so what we're going to do is you're going to grab your calculator. In y1, you're going to write 2x squared plus 5. Okay, in the graph portion as though you were going to graph it. We're not actually going to graph it, but go ahead and put that into y1. And then go back to the regular screen where you can type things in and add and subtract and so forth. I'm going to write in here, I'll write it in purple. You don't need to write this down, but this is what your calculator is going to say, okay? So what we're going to do is we're going to actually tell the calculator to add up these values, but I don't really care what the specific values are. All I really care about what's the sum of them, right? I just want to know what they are added together. In the regular screen in your calculator, you can tell your calculator to do y1 of 0 plus y1 of 1/2 or 0.5 plus y1 of 1 plus y1 of 3/2 or 1.5. And then when it's all said and done, you can tell your calculator to multiply this by 0.5 or by 1/2. Now, do you guys remember how to get to y1? Okay. Hit vars, y vars, function, and then you see y1 right there. Did you guys, everybody find it? That's how you get to y1. So
Then you do parentheses.
exactly. So it looks just like the function notation that you use in written form. Exactly. So the y vars you get to by hitting vars, y vars, function, y1. That's where you get it from. And you can repeatedly add that. And you could do this, obviously, for a lot of points pretty quickly. You can use the table. It wouldn't hurt to use the table. You just have to be really careful to keep all of your decimal approximations as you go. Now, this particular one, they're not ugly decimals, but sometimes they are. Imagine if you were doing something that was like a sine graph or a natural log graph or something, or e to the x. The approximations are much messier. These are actually all whole number or intervals of 0.5 values, so it wouldn't be bad if you just did these by hand and figured it out, like using your table or just plugging the numbers in flat out, what they are. So
once you get to y bars and you get here, you put push enter or do you
Okay, press enter. Parentheses. And then whatever value it is you want in there. So,
13.5.
So is it supposed to look like this?
you just don't need the last plus, because that was it, right? Or has the last one. Yep, and so hit enter. Did you get an answer, Luke? Is that before or after you multiply by 0.5?
After that.
Okay, so 13.5 is the final answer for this. Does anyone else second that? That's what you got. Now, this is, we're going to do this out of order. I'm going to jump to part C, and we're going to do the right endpoints next. And the reason we are is because in your calculator, you've already got all of what you need, almost, to do the right endpoints. So I do expect that you're going to write down what this actually would look like. That is, it needs to be the 1/2, and that you're going to start with f of 1/2. You're going to do f of 1, f of 3/2, or you can do decimal notation, of course, plus f of 2. So that I do expect that you're going to write down on the paper for me, all right? After that, your calculator can do the grunt work, the little pieces that it needs to do to calculate that. If you've already entered this into your calculator one time, which you did on part A, you can actually go back into that and edit what you've got. So if you'll hit second enter, it'll pull up the last line of text that you typed. Okay? So if you hit second enter, it should pull back up this piece that I've got sort of written in here in purple. That is before you multiply by the 0.5 or however. If you did it 2 steps back, do second enter twice. It'll pull up the second line back. It'll do that for a little while anyway. And all you need to do is change this y1 of 0 to say y1 of 2. Because that's the only one that's different down here. Okay, so compare this first line with this line right here at the very end. The only difference, right, the f of 1/2 match, the 1s match, the 3/2 match. The only difference is that instead of f0, you have f2, f of 2.
So as far as work goes, you just expect us to write that out.
Mhm.
X equals 1/2.
Yep,
And you can put that.
exactly. And if you want to write more out, you can, but at the very least, you need to show me this particular line that I've got written here underneath C. Okay? After that, did you get an or get a value? What did it work out to? 17.5.
Question.
Yeah.
For the midpoint one, would that be the same as putting those two together and dividing by 2?
It depends on the curve that you're working with. If it were a straight line, yes. Otherwise, no. Yeah. All right, let's take a look at doing the midpoint one. That one is a little bit more tedious to write out. And you can't just use what you did already in your calculator point blank and just replace the 0 with the 2. So for the midpoint, you still have the 1/2. But taking a look back over here, we need to figure out what the midpoints are of these intervals. So what is the first midpoint? 0.25 or 1/4. Okay, I'm going to use decimals because I haven't yet since you suggested it. So the first one's 0.25. What's the second one? 0.75. The third one? 1.25. And the fourth one? 1.75. Perfect. So over here with your function, you can write f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. You can even go back in if you want to, and you can manipulate what you did on the line before. You're going to have to change all 4 of them instead of just changing one of them. But it keeps you from having to do the keystroke of pulling up y1 every time, so that might be helpful.
You
15.25.
get that as well?
Mm-hmm, I did. Does that match what you guys are getting? Look good? All right, I want to make sure. On your homework, as it's listed at the bottom, what does it say? Somebody tell me what it says on the homework.
3, 6, and 7?
Yes, and on the 7, does it say n equal 4 next to it?
Yep.
Okay, good. So if you're checking the back of the book on number 7, it won't match because I've changed the number of rectangles. I don't remember what the book has, but I changed it to be n equal to 4 rectangles. Okay? All right, so 4.3 you should have done when you come to class next time, all right? It's just a few problems, agreed? Yeah, agreed.